Welcome to Draw the Logic, where we make complex ideas visual. In this video we build a complete, ground-up understanding of attention, the mechanism that powers every modern AI system, from machine translation to GPT-4, vision transformers, and beyond. Before attention existed, sequence-to-sequence models used recurrent neural networks. They encoded an entire source sentence into one fixed size vector, a severe bottleneck. The RNN reads tokens one by one, updating a hidden state at each step. Everything, all 8 words, must compress into one tiny fixed vector. For long sentences, early tokens lose their influence entirely. 3 fatal flaws: catastrophic forgetting, no parallelism, and a bias towards sentence-ending tokens. Attention was invented to fix all 3. The idea behind attention is simple. Instead of one fixed vector, let the decoder look directly at every encoder state and decide how much attention to give each one. Every element has a query, what it is looking for. Every element broadcasts a key, what it contains, and a value, the actual information it will share. The query and every key produce a similarity score. After softmax, those scores become weights that sum to 1. The output is the weighted average of all values, a rich, context-aware blend of the most relevant information. Bahdanau attention was the first modern attention mechanism. Published in 2014 for neural machine translation. 4 encoder hidden states, 1 per source word. Bahdanau uses the previous decoder hidden state to compute alignment. Each encoder state is scored against the previous decoder state using a small feed-forward neural network with a TAN activation. This produces a raw alignment score for each position. Scores are normalized through softmax to produce attention weights alpha. The context vector CT is the weighted sum of all encoder hidden states. 3 key characteristics: previous decoder state, a learned feed-forward alignment model, and global attention. Luong simplified Bahdanau's approach a year later, replacing the costly feed-forward alignment with a dot product. The critical change: Luong uses the current decoder state, not the previous one. Alignment is just a dot product. Multiply the encoder state by a weight matrix. Then dot with the current decoder state. Much faster. Pure matrix multiplication. No extra neural network. Luong also introduced local attention. Instead of attending all source words, the model can focus on a sliding window, giving more flexibility for long sequences. Let's compare the 2 architectures directly. Bahdanau uses a trained feed-forward network and the previous decoder state. Expressive but slow. Luong uses a simple dot product and the current state. Fast and easily parallelized. Luong's dot product idea directly inspired the scaled dot product attention in the 2017 Transformer paper. The 2017 Transformer formalized attention into 3 matrices: queries, keys, and values. The best way to understand them is through a database analogy. 3 steps. Compute dot products between every query and every key to get similarity scores. Apply softmax to get attention weights. Then blend the values by those weights to produce the output. Q, K, and V are linear projections of the same input X through 3 separate learned weight matrices. Here is the complete attention formula, as introduced by Vaswani et al. In the 2017 paper, attention is all you need. Attention of Q, K, V equals the softmax of Q times K transpose over root dk, multiplied by V. The scaling factor looks like a minor detail, but it is critical for training stability. Without scaling, softmax receives huge inputs. The output collapses to a one-hot distribution. One token gets all the attention weight. Gradients through softmax become nearly 0. Halting training. Dividing by the square root of dk stabilizes variance. The softmax output stays smooth. Multiple tokens contribute. Gradients flow cleanly. And training converges. Let's walk through a concrete numerical example with 3 tokens to see every step. The raw score matrix, each I.J. entry is Q_I.K_J. After softmax, each row sums to 1. Row, cat, shows weights 0.09, 0.25, 0.66. Cat strongly attends to mat. Each output token is the weighted average of all values. The outputs are 2.58, 2.85, 2.95. Risha. Context-aware representations. In self-attention, Q, K, and V all come from the same input sequence. Every token can look at every other token within the same stream. This resolves ambiguity. For example, bank, meaning river edge versus financial institution, depends on surrounding words. In cross-attention, queries come from one sequence, the target, while keys and values come from a second sequence, the source. This bridges 2 modalities: translation, image captioning, or grounding a generated answer in a reference document. A single attention head tends to focus on one aspect of the input. Multi-head attention runs H attention operations in parallel, each in its own subspace. Each head uses D_model divided by H dimensions. So the total computation equals a single full-width head, but with H times the representational variety. Vaswani used H equals 8 heads. Modern models use 32 to 128. For language generation, the model must not see future tokens during training. Masking enforces this causal constraint. The mask is a lower triangular matrix. Green check marks are allowed attention pairs. Red -infinity entries are set to -infinity before softmax, becoming exactly 0 after exponentiation. Row, cat, can attend to itself and earlier tokens, but is completely blind to sat and mat. They haven't been generated yet. During training, masking allows all positions to be predicted in parallel. During inference, generation is still sequential, one token at a time. The mask makes both modes mathematically identical. Attention has no built-in sense of order. 2 supporting mechanisms fix this and stabilize deep training. 4 encoding strategies. The original transformer used fixed sinusoidal encodings. Modern models prefer rope, rotary position embedding, which encodes relative positions as rotations and generalizes to sequences longer than those seen during training. Every sublayer in the transformer uses add and norm. Add the sublayer output to its input via a residual skip, then apply layer normalization. Residuals give gradients a direct path through depth. Layer norm keeps activation stable across dozens of layers. During auto-regressive generation, each new token must attend to every previous token. Recomputing all keys and values from scratch at every step would be catastrophically slow. The KV cache stores previously computed keys and values in GPU memory. For each new token, only the new queue needs computing. Attention queries the cache rather than recomputing everything. The problem: at 128,000 token contexts, the uncompressed KV cache can balloon to 488 gigabytes, beyond any single GPU's memory, even when it fits. Reading the entire cache for every new token saturates memory bandwidth and forces compute cores to sit idle. 4 architectural strategies address the KV cache problem, each with a different trade-off between expressiveness and memory. MHA keeps full keys and values for every head. MQA shares one key value pair across all heads. Fast but lower quality. GQA groups query heads and shares 1 KV per group. The sweet spot used by Llama. DeepSeek's MLA compresses keys and values into a tiny latent vector using low rank projection, achieving a 93% reduction in cache size without sacrificing quality. The attention matrix is quadratic in sequence length. But the bottleneck is not arithmetic. It is memory bandwidth. FlashAttention fixes this with tiling. Naive attention writes the full n-squared matrix to slow GPU HBM memory 4 times. Compute cores stall waiting for data. FlashAttention loads small tiles of Q, K, V from HBM into the fast on-chip SRAM. The entire attention computation for that block, multiply, scale, mask, softmax, happens inside SRAM. Only the final output goes back to HBM. Memory footprint drops from quadratic to linear. FlashAttention has 4 generations. V1 introduced tiling. V2 improved warp partitioning. V3 exploited Hopper's async tensor cores. And V4 targets Blackwell, reaching nearly 1.2 petaflops of throughput. FlashAttention accelerates the quadratic computation, but it doesn't change the math. Linear attention replaces softmax with a kernel feature map that allows the computation to be fundamentally O of n. Linear attention approximates the similarity metric as the dot product of 2 decoupled feature maps phi of q and phi of k. This makes the computation separable. By applying matrix multiplication right to left, multiplying phi of k transpose by v first, we get a fixed size d by d state matrix instead of n by n. This state acts just like a recurrent hidden state, making per token decoding O of 1. State space models come from control theory. They model sequences through continuous differential equations. Mamba made SSMs competitive with transformers. Mamba 1 introduced a selection gate to filter irrelevant tokens, the first SSM to rival transformer benchmarks. Mamba 2 proved the mathematical duality between SSMs and linear attention, unlocking tensor core efficiency. Mamba 3 adds complex valued states and MIMO, halving the required state size. Attention is the foundational layer of modern AI across every data modality and task domain. From NLP to vision, speech, reinforcement learning, and graph networks, attention provides a universal mechanism for relating any element to any other element in a structured data stream. Attention is powerful, but it has well-documented pitfalls that every practitioner must understand. 5 key pitfalls. Attention weights are not explanations. Many heads are redundant. The cost is quadratic. There is no built-in structural bias. And deep transformers are notoriously sensitive to training configuration. Attention began as a fix for machine translation in 2014 and became the foundational layer of modern AI in less than a decade. Its story is one of continuous mathematical and hardware co-design. From additive scores to quadratic kernels. From gigabyte KV caches to 93% compressed latents. From sequential hidden states to petaflop tiled tensor cores. Attention is the architectural language of modern intelligence. If this video gave you a clear picture of attention, from its origins to MLA and FlashAttention, please like, share it with someone learning AI, and subscribe to Draw the Logic for more visual deep dives every week. Thank you for watching.